Hello and welcome to the second module of the course Basics of Semiconductor Devices and Technology. In this module, we are going to review the main physical ideas and experimental facts that defied classical physics and led to the birth of quantum mechanics. The introduction of quantum mechanics was prompted by the failure of classical physics, as we know, in explaining a number of microphysical phenomena that were observed at the end of 19th and early 20th century, which I briefly touched based on the previous module. In this module, I'll try to review some of these aspects which will set the foundations for the origin of quantum mechanics, which I will cover from the next module. Okay, so at the end of 19th century, physics consisted essentially of classical mechanics, which was the theory of electromagnetism and the thermodynamics. Classical mechanics at that time was used to predict the dynamics of material bodies, which means if something is in motion and if you know the current state, position, momentum, direction, you can predict the future of the object, the body, or you can predict where the body is heading to be, and you can also predict where the body will be, let's say at a certain time in future. And the Maxwell's electromagnetism provided the proper framework to study the radiation or the behavior of radiation. At that time, matter and radiation were described in terms of particles and waves respectively, which means that the matter was considered as particle and radiation was always considered as the wave. And as far as the interaction between the matter and the radiation is concerned, they were very well explained with Lorentz force or by thermodynamics. So the classical physics was so successful, classical physics in terms of classical mechanics, classical theory of electromagnetism, and thermodynamics, that people started believing that the ultimate description of nature has been achieved. And it seemed to people, the physicists at that time, that all known physical phenomena could be very well explained within the framework of general theories of matter and radiation. In this, I did not touch base on the Newtonian mechanics, the classical mechanics, because that was considered to be already established from the Newton's time. So that's a parallel thread of modern physics where Einstein came in and he said that there are certain flaws in Newtonian mechanics and those laws are not valid when objects move at very high speeds, like speeds close to speed of light. Even the concept of light was not very well known at that time, and light was considered to be some radiation, some wave, which again was based on the hypothesis from Maxwell's equation that if the speed of radiation is same as light, then later on people started correlating that light would also be a radiation. So at the beginning of 20th century, there were certain aspects which could be challenged, which were challenged, that were following. I mean, one, as I told you, that the relativistic domain, Einstein's 1905 theory of relativity actually showed that the validity of Newtonian mechanics ceases at very high speeds. High means speeds which are closer to light. And then the microscopic domain, which when as soon as new experimental techniques were developed to probe aspects at the atomic and the subatomic level, and to probe the atomic and the subatomic structures, it turned out that classical physics fails miserably in providing a proper explanation for several newly discovered phenomena, which I'll talk about in this module in greater detail. And therefore, it became evident that the validity of classical physics ceases at the microscopic level, and the new concepts had to be invoked to describe some of these microphysical phenomena. Let's say, for instance, the structure of atoms and molecules and how light interacts with all of them. So, in fact, this was a key question at that time, that what is the structure of atoms, molecules, and how, for instance, light would interact with atoms and subatomic particles. So the first real breakthrough came in year 1900 when Max Planck introduced the concept of quantum of energy. In his work, apparently to explain the phenomena of blackbody radiation, and I'll briefly summarize later that the blackbody radiation was predicted earlier by, or basically the behavior was shown by other people, and then various people started explaining the aspect, and it was Max Planck who, in his effort to explain the phenomena of blackbody radiation, he succeeded in reproducing the experimental results which many people had produced. And that happened only after postulating that the energy exchange between radiation and its surrounding takes place in discrete or quantized amounts. He argued that the energy exchange between an electromagnetic wave of frequency, let's say nu, and matter occurs only in integer multiples of h nu. Here h is the Planck constant, and the energy h nu he called as the energy of quantum. The quantization of electromagnetic radiation apparently turned out to be an idea with far-reaching consequences, and you will see that many discoveries or hypotheses subsequently were based on this particular empirical assumption which Planck took. Again, many of these ideas were hypothesis or empirical assumption, and gradually people realized that those assumptions or hypothesis has such far-reaching consequences that not only they turned out to be universal reality or fundamental realities, or some of these become universal constants, but they also gave birth to a new thinking and gave birth to what we know today as quantum mechanics. So, as far as the chronology is concerned, in 1900, the blackbody radiation was explained by Planck, and apparently Planck's idea, which gave an accurate explanation of blackbody radiation, prompted a lot of new thinking with other people. For example, in 1905, Einstein provided a powerful consolidation of Planck's quantum concept in order to understand the photoelectric effect. Photoelectric effect was also observed by, or the phenomena, the experimental phenomena was observed by many people, but it was only Einstein who could explain it by borrowing the idea of quanta from Planck's work. So Einstein recognized that Planck's idea of the quantization of electromagnetic wave must be valid for light as well, and Einstein was working on the concepts of light or understanding light since some time. So following Planck's approach, he posited that light itself is made of discrete bits of energy, and again that was his assumption, that was his hypothesis. These discrete bits of energy you can think of as tiny particles, which he called photons, each of having energy h nu, where nu being the frequency of the light. Now, the introduction of photon concept enabled Einstein to give an elegantly accurate explanation of the photoelectric problem, which had been waiting for a solution since its first experimental observation by Hertz in 1887. So you can imagine this is 22 years, 23 years of long wait before it can be explained. Another seminal breakthrough was due by Niels Bohr that happened immediately after Rutherford's experimental discovery of atomic nuclei in 1911. And again, Rutherford gave an atomic model in 1911, and Niels Bohr basically combined the two things, discovery of atomic nuclei or the nucleus, as well as Rutherford's planetary model. He also combined Planck's quantum concept and Einstein's photon concept. And using this, Bohr introduced in 1913 his model of hydrogen atom. In this work, he argued that atoms can be found only in discrete states of energy. That's the interaction of atoms with radiation, or the emission or absorption of radiation by atom, must take place only in discrete amounts of h nu, because it results from transition of atom between its various discrete energy states. Again, later, the birth of quantum mechanics, or the birth of the mathematical formulation, you realize later that was again born by the fact that many people were not so happy with just an hypothesis being in place and not a strong theoretical formulation or foundation which actually explains it. So basically his work provided reasonable explanation to several outstanding problems, such as atomic stability, atomic spectroscopy. Many of those things were experimentally observed, but it was not clear how to explain it, because often people try to explain using classical understanding of physics, which was pretty well established at that time, and it's very difficult. If something is established since 100 years, it's very difficult to change that. Then in 1923, after a longer period, Compton made an important discovery, and that gave the most conclusive confirmation for this particle aspect of light, or this quantum aspect of light. So he scattered X-rays with electrons, and he confirmed that X-ray photons, X-rays are again light beyond visible spectrum. So he confirmed that X-ray photons behave like particles with momenta h nu by c, where nu is the frequency of the X-rays. So till this time, all these series of big breakthroughs, right? So we are somewhere here. And I'll tell you that, this was all the time where, till when the hypotheses were made, the explanations were given for experimental observations, but the mathematical formulation was yet not there. So all these breakthroughs due to Planck, Einstein, Bohr, and Compton, they gave, birth to the theoretical foundations. It was not theoretical foundation which was in place, but they all established the facts which are required for somebody to come up with a theoretical foundation, which was later on called quantum mechanics. So basically the phenomena that we talk about is quantum physics, or the physics at the microscopic scale is quantum physics, and the theoretical formulation is quantum mechanics. So in 1923, I would say, as the things were not bad enough for classical physics, in 1923, de Broglie introduced another powerful idea, or the concept, that classical physics, after that could not come back. What he did, he postulated that not only does the radiation exhibit particle-like behavior, but conversely, material particles themselves behave wave-like behavior. And this concept, in fact, was confirmed experimentally in 1927 by Davison and Germer, where they showed that interference patterns, which is we all know from the older times, or those people knew from the older times that was a property of wave, can be obtained with material particles such as electrons as well. And um, and then he basically hypothesized the wave particle duality, and that was further used in establishing the mathematical formulation for quantum mechanics. So, although Bohr's model for the atom produced results that agree well with experimental spectroscopy, it was criticized for lacking the ingredient of a theory. Like the quantization scheme introduced by Planck in 1900, the postulates and assumptions adopted by Bohr in 1913 were quite arbitrary. I mean, there was no theoretical framework already established on which they established some of these ideas. These ideas were random, though they fit into experimental observations, but the ideas were random, and they did not follow the first principles of any theory. And therefore, it was the dissatisfaction with the arbitrary nature of Planck's idea and Bohr's postulate, as well as the need to fit them within the context of a consistent theory, which apparently prompted Schrödinger and Heisenberg to search for theoretical foundation underlying these new ideas. So by 1925, their efforts paid off, and they skillfully welded the various experimental findings as well as Bohr's postulate into a refined theory, which is called quantum mechanics. So, in addition to providing an accurate reproduction of the existing experimental data, this theory turned out to be, an astonishing, reliable prediction, or having the power to predict many of these behaviors, which enabled to explore and unravel many uncharted areas of microphysical world. So far people tried to basically explain the observations, but now here you have a theory, or here you have a mathematical formulation in place which you can also use to predict the behavior. Of course, there are certain boundary conditions in which you will predict, which I'll talk about later, like Heisenberg's uncertainty principle. But now you have a mathematical formulation which you can use to predict the behavior, and that's why you use the term mechanics, because we had classical mechanics, which was used to predict the behavior of classical objects. If you know their current state, direction, speed, and so on, you can predict their behavior, you can predict their future behavior, you can predict where they are heading to. And now you have a mathematical formulation using which you can predict the behavior of these microphysical entities, and under certain boundary conditions like Heisenberg uncertainty principle, you can predict where they are heading to. Now, also, in addition to providing an accurate reproduction of the data, as I said, that you can predict, for instance, that how they all will behave when let's say several microphysical objects are in the system together. So I would say this new theory had put an end to almost 25 years of patchwork, which started from Planck and ended with Schrödinger and Heisenberg. And apparently it was dominated by the idea of Planck and Bohr, which later became known as the old quantum theory. So the first formulation, the mathematical formulation which was called the matrix mechanics, was developed by Heisenberg in 1925 to describe the atomic structure starting from the observed spectral lines. Again inspired by Planck's quantization of wave and by Bohr's model hydrogen atom, Heisenberg founded his theory on the notion that only allowed values of energy exchange between microphysical systems are those that are discrete or quantized in nature, or you call them quanta. Now, expressing dynamical quantities such as energy, position, momentum, angular momentum, in terms of matrices, he obtained an eigenvalue problem that describes the dynamics of microscopic systems. He basically came up with this diagonalization of Hamiltonian matrix, which yields the energy spectrum and the state vectors of the system. And as a result of that, matrix mechanics was quite successful in accounting for discrete quanta of light emitted and absorbed by atom. Again, this all was based on Planck's idea and Bohr's hypothesis. So, till things were still, for discrete kind of systems, or single body systems, or things where you have discrete amount of transfer and let's say one photon transfer or of that kind in nature. This was further improvised by Schrödinger. I mean, of course, Schrödinger is working in parallel, and that's the second formulation called wave mechanics by Schrödinger in 1926, and that was basically based on the generalization of de Broglie postulate. This method was more intuitive than the matrix mechanics, and it describes the dynamics of the microscopic matter by means of wave equation, which we all know as Schrödinger equation. I'll talk about Schrödinger equation in the next module, and the quantum mechanics that we will study in this course will be mostly based on the wave mechanics or using the Schrödinger equation. Rather, following the matrix eigenvalue problem Heisenberg, which is not so intuitive, and therefore visualization the problem becomes a little tricky. So to do this, Schrödinger apparently obtained a differential equation. As I said, that equation is the Schrödinger equation, and the solution to this equation yield the energy spectrum, not the discrete energy states, energy spectrum, and the wave function of the system under consideration. And this wave function is so useful, so powerful, that you can predict many aspects of a system or a microphysical system. The solution of this equation, I'll be talking about this in detail later. So after what happened, in 1927, so wave equation was already there in place, but in 1927, Max Born proposed his probabilistic interpretation of wave mechanics, and that's where the probability densities using the wave function came into picture. And then finally, in 1928, Dirac basically presented his Dirac notation for explaining the quantum mechanics, where the quantum mechanics deals with the abstract objects such as kets, bras, and operators. The representation of Dirac's formalism was in continuous basis, like the position or the momentum representation, which again gives back in continuous basis. It will give back the Schrödinger wave equation, and in discrete basis it will give you the Heisenberg's matrix formulation. So in this context, the approach of Schrödinger and Heisenberg was very well covered in Dirac's notation. Then finally, so far we're talking about quantum mechanics, and then Dirac in 1928 combined special relativity with quantum mechanics, and he derived what is known today as relativistic quantum mechanics. relativistic quantum mechanics also predicted at that time the existence of antiparticles, positrons. In fact, many of these particle physics aspects, or the foundation of particle physics, was based on the discovery, or the predictions made based on relativistic quantum mechanics. In fact, the positron was experimentally discovered after its prediction in 1928. It was experimentally discovered in 1932, and that established the predictions and the aspects related to relativistic quantum mechanics. So let's start getting into the details of some of these aspects. I tried to give you an overview of what happened in those 25-30 years, and let's get into the details of some of these aspects, like blackbody radiation, which is related to blackbody radiation, photoelectric effect, some of these aspects which are related to the wave nature of the particle, or the particle nature of the wave, and then I'll talk about the Heisenberg uncertainty principle and some of these aspects in this module, and then we'll use this to establish the mathematical formulation and application of that mathematical formulation, which is the quantum mechanics, from the next module. So the very first aspect of the origin of quantum physics, or the origin of quantum mechanics, is the particle aspect of radiation. Now, according to classical physics, a particle is characterized by an energy E and momentum P. Whereas, as we all know, that a wave is characterized by an amplitude. A wave will have, a certain amplitude, and it will have a wave vector which is k, where k is nothing but 2 pi by lambda, and you know what is lambda, which is the length from here to here, right? And it also specifies the direction of the propagation of wave, which is represented by this vector quantity. Now, in classical physics, particles and wave exhibit entirely different behavior, and for that reason, particle and wave properties are mutually exclusive. And in classical physics, we should note that the wave can exchange any continuous amount of energy with particles. So in this part, which is related to the particle aspects of radiation, we will see how these rigid concepts of classical physics failed in explaining a number of microscopic phenomena such as blackbody radiation, the photoelectric effect, and the Compton effect. And these observations, which are for blackbody radiation, photoelectric effect, Compton effect, and so on, shown that you need something beyond the classical understanding of interaction between wave and the particle. So the first one is blackbody radiation. It basically the aspects people started observing, in fact, by mid of 19th century. The question here is that how radiation interacts with matter. This question people started asking this question by mid of 19th century, and the observations were so different than what one could imagine based on the understanding from the classical physics. For instance, let's say in this case, when you heat a solid object, the object will glow, and emit thermal radiation. That's something we all have seen, and possibly people would have seen at that time. Metallurgy was there, melting was in place, heating was in place. So people would have observed this, that you heat something, it glows, and as you increase the temperature, the color of course changes. So when you heat an object, it will emit radiations, and the radiation color will also change. For instance, if you heat it moderately, it will be red, then it will be yellow, and if you heat it so high, it will be white. And if you measure it, the thermal radiation emitted by glowing solid objects would consist the continuous distribution of frequencies ranging from infrared to ultraviolet. The continuous pattern of distribution spectrum, which was observed at that time, is in sharp contrast to the radiation emitted by heated gases. In fact, many of these experiments happened on heated gases. And it was quite established that you heat a gas, and depending on the temperature, you have one frequency emitted, and that one frequency is a function of temperature, right? And that's why the radiation emitted by gases has discrete distribution spectrum, a few sharp narrow colored lines with no light in between. Now, understanding the continuous character of the radiation emitted by a glowing solid object constituted one of the major unsolved problems during the second half of 19th century. All attempts to explain this phenomena by means of available theories of classical physics, which are statistical thermodynamics and classical electromagnetic theory, ended up in miserable failure. So this problem consisted in essence of specifying the proper theory of thermodynamics that describes how energy gets changed between radiation matter. In fact, people were still thinking about that possibly the thermodynamics, or the theory, the underlying theory behind thermodynamics, need to be redefined to explain how energy is exchanged between matter and radiation. And after a very long time, from this mid 19th century to early 20th century, when Planck introduced this concept of quanta, which gave birth to this new field. I mean, people realized that okay, you don't have to redefine thermodynamics, you have to think completely differently. So let's talk about what were the observations, right? So in terms of observations by mid 1800, a lot of experimental data about blackbody radiation was obtained on various objects. I mean, almost everything else was heated and spectrums were extracted. And all these results show that at equilibrium, the radiation emitted had a well-defined continuous energy distribution. From continuous, I mean, if you plot the energy distribution as a function of frequency, what you get is all the way from low frequencies to high frequency, you get a continuous distribution. And each frequency, for each frequency, there would be an energy density, which neither depends on chemical composition nor depends on the object shape or size, but it only depended on the temperature of the object. Or if it is a cavity which you design to basically get these emissions, it only dependent on the size of the cavity walls, right? So this trend was universal, and it was not a function of anything else but only the size of the only the temperature, sorry, only the temperature of the cavity wall. The energy density shows a pronounced maximum at a given temperature. So if you plot this for different temperatures, it will look like this. And as a function of temperature, you see these maximas. And this peak increased with increasing temperature. Or in other words, the peak of the radiation spectrum occurs at a frequency that is proportional to the temperature. I'll show that in the next slide. And in fact, this is the underlying reason behind the change in color of a heated object as its temperature is increased. I mean, as you increase the temperature, it turns red, then yellow, then white. And it turned out that the explanation of blackbody spectrum was not so easy, and you cannot basically explain it based on the classical thermodynamics or by any redefined thermodynamic principles. So there were a number of attempts to explore this, to understand the origin of this continuous character of radiation. And I have listed few most serious attempts. For instance, Stephen was in 1879. J. Stephen tried to extract the total power, which is nothing but the area under the curve, and try to come up with a formula which explains the total power under the curve. And he could come up with a nice empirical relation which very much gave the total area under the curve of this spectrum. But of course, this was not sufficient to explain the shape of this spectrum, right? But this relation, for instance, from Stephen was known as Stephen-Boltzmann law, and that helps a lot in telling the total power per unit surface area radiated by a glowing object if the object is heated at temperature T. Here, sigma is this Stephen-Boltzmann constant, and typically the sigma value is 5.67 into 10 to the minus 8 watt per meter square per Kelvin to the power 4. And A is another fitting parameter, and if A is 1, we are talking about a perfect black body. If it is less than 1, it's not a perfect black body, but A will always be between 0 and 1. So other than Stephen and Boltzmann, Wien's work and subsequently Rayleigh's work basically were very close to predicting the behavior. But again, that was all based on the ideas from or by combining the thermodynamics principle or the Maxwell's theory, and were yet not in terms of, or yet not there in terms of explaining the true physical phenomena which is responsible for this kind of behavior. So Wien, for instance, obtained an energy density per unit frequency function, which I will show in the next slide. And here, for instance, A and beta are the fitting parameters, and what was shown that the U, which is the energy density per unit frequency based on the Wien's formula, only fits the high frequency data. So this is the Wien's part. The other one, so I mean, again, Wien used thermodynamic arguments. He took the Stephen Boltzmann law and kind of obtained this function, which would fit to some part of this spectrum, but not to everything. The other bigger work, which actually set the foundation for Planck's work, was actually by Rayleigh and Jean, and I'll talk about that, how it happened. But before that, if you see this spectrum and you see that the Wien's formula would fit nicely to a certain part of the curve, and the Rayleigh and Jean would fit to the certain part of the curve, but there was nothing which could nicely explain the entire thing other than the Planck's law, which I'll talk about later. Right, so after the Wien's formula came the Rayleigh's energy density distribution. So Rayleigh was trying to focus on understanding the nature of electromagnetic radiation inside the cavity. So he considered that the radiation, to consist of standing waves having temperature T with nodes at the metallic surfaces, and these standing waves, he argued, are equivalent to harmonic oscillators. For they result from the harmonic oscillations of a large number of electrical charges, which are electrons that are present in the wall of cavity, and therefore he assumed this is like a harmonic oscillator. So when the cavity is in thermal equilibrium, the electromagnetic energy density inside the cavity must be equal to the energy density of charged particles in the wall of the cavity, and the total or the average total energy of radiation leaving the cavity can be obtained by multiplying the average energy of oscillations by the number of modes, which are the standing waves of the radiation in the frequency interval of nu to nu plus delta nu. And so that's how you get this formula, n nu equals to 8 pi nu square by c cube. I have skipped the derivation for this part, but again, as I said, that you here the assumption is that the cavity is behaving like a harmonic oscillator, and in thermal equilibrium the electromagnetic energy density is equal to the energy density of the charged particles, and therefore the total energy of radiation is nothing but the number of modes which are present inside the cavity, which again depends on the dimensions of the cavity, and the average energy in frequency nu to nu plus delta nu. In this formula, c is nothing but the speed of light, and the quantity 8 pi nu square by c cube dV, if I multiply this by dV, would give the number of modes of oscillation per unit volume in frequency range from, as I said, from nu to nu plus d nu. So if now if we multiply this by the average energy, or what will be the electromagnetic energy density in the frequency range nu to nu plus del nu? That will be by, so we are looking into this parameter, and if you multiply this with the average energy is, or the expected energy, right, we get the energy density or the spectrum that we're looking for. Now, what is this energy, average energy, that we get from the equipartition theorem, again, which comes from the thermodynamic principle of classical thermodynamic principle. So, according to equipartition theorem of classical thermodynamics, all oscillators in the cavity have the same mean energy, irrespective of their frequencies, and therefore you can use this formula for calculating the mean energy of all the radiations or all the oscillations inside the cavity. And it turns out to be nothing more than kT. So you know that kT is the mean energy of associated with any system, where T is the temperature, average temperature across that system. So now again, if you see, the assumption here is that the standing waves which are formed inside the cavity can exchange any amount of energy with the matter. That's the assumption here, and that's why you get this kind of formula from the way it is derived. And so the energy of the radiation is continuous, and therefore you kind of in this formula for calculating the average energy, you integrate across the entire energy range from 0 to infinity. Now this is the key here. If you assume that the exchange is continuous in nature and any amount of energy can be exchanged with matter, here for calculating the average energy, you integrate in the continuous domain from 0 to infinity to get the average energy, which is kT. And we'll see that this is the only small change which the Planck did and got a very different formula. So as a result of this, Rayleigh-Jeans could get this formula, which was fitted well to one part of the spectrum, but it failed to fit the other part of the spectrum. So before I get into the Planck's energy density distribution, I must highlight that the origin of this failure can be actually traced in the derivation of the average energy, as I already highlighted. It was founded that this error in the assumption of energy exchange between radiation and matter, which was assumed to be continuous, or any amount of energy can be exchanged, led to not fitting of this behavior or this characteristic into the complete spectrum. So Rayleigh-Jeans formula, which was not able to predict the high frequency behavior, and therefore the existence of the ultraviolet frequencies could not be confirmed. In fact, that was called the ultraviolet or UV catastrophe. In Planck's work, by interpolating between Wien's rule and Rayleigh-Jeans rule, Planck in 1900 successfully, or kind of succeeded in avoiding the UV catastrophe and proposed a more accurate description of the blackbody radiation. So unlike what Rayleigh assumed, Planck's assumption was that energy can be exchanged between radiation and matter only in discrete entity. So he then postulated that the energy of the radiation, let's say of frequency nu, emitted by the oscillating charge from the walls of cavity must come out in integral multiples of h nu. So if then the total energy will be n times h nu, where h nu is the quanta and where n could be any number from 1 to any finite higher number. As I have mentioned earlier, h is the universal constant, or h turned out to be universal constant, and h nu is the energy of quanta or energy of quantum of radiation, where nu represents the frequency of oscillating charge in the cavity's wall, as well as the frequency of the radiation emitted from the walls, because the frequency of radiation emitted by an oscillating charged particle is equal to the frequency of oscillation of the particle itself. And that is the energy of an oscillator of natural frequency nu, which corresponds to the energy of a charge. and therefore this energy must be integral multiple of h nu. Um, so classical mechanics puts no restriction whatsoever on the frequency and hence on the energy an oscillator can have. The energy of oscillators such as pendulum, mass spring systems, electric oscillators varies continuously in terms of frequency. But that was not the case in Planck's quantization rule, or for the energy in case of Planck's postulate. So now, how this formula came up, you assume that the energy of an oscillator is quantized. Planck showed that the correct thermodynamic relation of the average energy can be obtained by merely replacing the integration by, integration corresponds to an energy continuum by discrete summation, which corresponds to the discreteness of these oscillators' energies. So you remember in the in Rayleigh-Jeans approximation of average energy, he used this formula for calculating the average energy of the spectrum, whereas or the oscillations, whereas in Planck's case he assumed that the transfer of or the exchange of energy between matter and radiation should be discrete in nature, and it should be of the order of h nu, and therefore he assumed that the this average energy must not be calculated by integrating the function, but by summing the function through these discrete entities, having n moving from 0 to infinity. And the moment you sum this function, you get a very different relation for the average energy, right? So the energy density per unit frequency of radiation, which can be emitted from the cavity, would nothing be the formula that we have seen earlier times the average energy, which is extracted from the summation of various energy states or the energy distribution across the system. And if you plot this one, it very nicely fits into the spectrum that was experimentally seen when the value of h here is 6.626 into 10 power minus 34 joules second. This value gives perfect experimental fit, and that's why this value became a universal value and called Planck's constant. Now, if you want to calculate or obtain the energy density, which I told you earlier, the spectrum is continuous in nature, so you can integrate this, right? So if you want to calculate the total energy density, you have to calculate the area under the curve, and area under the curve is nothing but this function, which is u v t, and you integrate this from 0 to infinity, right, which is shown here, and what you get is 4 by c sigma t to the power 4. And if you calculate the value of sigma here, this value is same as what we had seen in the previous slide here, which was the Stephen-Boltzmann law. So in summary, the spectrum of the blackbody radiation reveals the quantization of radiation, notably the particle behavior of electromagnetic waves, the topic we started with. The introduction of the constant h, or the Planck constant, had indeed heralded the end of classical physics and the, I would say, dawn of a new era, physics of the microphysical world. stimulated by the success of Planck's quantization of radiation, and other physicists, notably Einstein, Compton, Broglie, Bohr, skillfully adapted the same quantization principle to explain a number of outstanding problems that had been unanswered for decades. With this, we'll move to the photoelectric effect in the next class, and I will see you all in the next class. Thank you.